Have you ever wondered how a computer can learn to predict something like the price of a house or figure out if an email is spam? I mean, it sounds super complicated, right? But what if I told you that underneath it all, there's this hidden and actually pretty simple recipe that makes it all work? Well, today we're going to pull back the curtain and uncover that very recipe.
So let's start with the big question you see here. How can a computer, which at its heart is just a really, really fast calculator, look at a bunch of data and somehow learn to predict stuff it's never even seen before? It's a fantastic puzzle, and we're going to solve it together, piece by piece, starting with an example you've definitely heard of.
All right, to kick things off, we're diving into what we'll call the prediction game. And we're going to ground this whole thing in a really tangible problem, figuring out house prices. We're going to use some actual data from Portland, Oregon, to see exactly how a machine starts to think.
Now have a look at this. This is literally all the machine gets to see. We call this our training set. You can think of it like a deck of flashcards for a student. For a house that's 2,104 square feet, the price is 400 grand. For one that's 1,600 square feet, it's 330 grand. The machine's entire job is just to stare at these examples and find the hidden pattern.
You know, in the world of machine learning, this kind of problem actually has a specific name. It's called a regression problem. Anytime your goal is to predict a number that can be anything along a continuous scale, like an exact price or a temperature or maybe a stock value, what you're really doing is regression. Okay, so we've got our data points. If you were to plot them on a graph, what's the most basic way you could try to capture the pattern? Well, you'd probably just try to draw a straight line through them, right? And that's exactly what the machine does. Our job now is to teach it how to find the one single best fit line out of, well, an infinite number of lines it could possibly draw. Now, I know when you see an equation like this, it can look a little intimidating, but don't worry. This is just the good old formula for a line from high school math. H is just the machine's prediction, its hypothesis, and X is our input, the size of the house. The most important parts for us are those two theta symbols. Just think of them as two little dials that the machine can turn. One dial moves the line up and down, the other changes how steep it is. The whole game is just tuning those dials to find the perfect fit. Okay, but that brings up a huge question, right? How in the world does the machine know which line is the best one? I mean, there are so many possibilities. It needs some way to grade itself to know if it's getting warmer or colder. And it does that by measuring its own unhappiness. It uses something called a cost function. It's actually pretty simple. For any line it draws, it just measures the total distance between its line and all the real data points. That total error, that's the cost. So a line that's way off has a really high cost, and a line that slices right through the middle of the points has a really low cost. The goal? Get the lowest score possible. So how does it actually find that lowest point? This is where a really cool algorithm called gradient descent comes in. The best way to think about it is to imagine you're a hiker standing on a mountainside, but it's completely foggy. You want to get to the very bottom of the valley, but you can't see it. All you can do is feel the ground right under your feet. So what do? You feel around, find the direction that goes downhill the steepest, and you take one step that way. Then you stop, feel around again, and take another step in the new steepest direction. You just keep doing that, step after step, until you can't go downhill anymore. That's exactly what gradient descent does. It just keeps nudging those dials always in the direction that makes the error go down the fastest until it finds the best possible line. Okay, so using lines to predict numbers is pretty powerful stuff. But what happens when the answer we're looking for isn't a number at all? What if the answer is just a simple yes or no?
Well, this brings us to a whole new type of challenge. On one hand, you've got regression, which asks how much, but on the other hand, you have a new problem called classification, which asks which one. Here, the answer isn't on a sliding scale. It's a fixed category, like spam or not spam, which we can just represent with a 1 or a 0. And you can probably see why our trusty straight line is just a terrible tool for this job. A straight line can shoot way up past 1 or dip way down below 0, and that just doesn't make sense for our problem. You can't have an email that's 150% spam, right? We need a function that's kind of forced to stay between 0 and 1. We need a whole new shape. And that new shape is called the sigmoid function. It's brilliant. No matter what number you put into this thing, a huge positive number, a big negative number, anything, it always squishes the output into a value somewhere between 0 and 1. And this is perfect because now we can think of the output as a probability. So if the model spits out 0.9, it doesn't mean 0.9 spam, it means there's a 90% chance that this email is spam.
So let's take a step back. It kind of feels like we have two totally different problems, right? We've got regression and we've got classification, and they seem to need two totally different solutions, a straight line for one and this S-curve for the other. But are they really as different as they look? I mean, it sure seems that way. A straight line model for house prices and this S-curve thing for spam. They solve different kinds of problems, they use different math. They've got to be two completely separate tools in the machine learning toolbox, right? Well, here's the big reveal. The crazy part is, no, they are actually just two different versions of one single, incredibly powerful idea, the generalized linear model, or GLM. It's like a master recipe that can cook up both of these models and a whole bunch of others just by swapping out a couple of key ingredients. So what is this master recipe? What's the secret sauce? It all comes down to just three core ingredients, three fundamental design choices you make. And these three choices can build not just the two models we've talked about, but a whole family of learning algorithms. And here they are. First, you make a simple assumption about your answer. Is it a number that could fall anywhere on a spectrum, kind of like a bell curve? Or is it a simple this or that outcome, like a coin flip? That's ingredient number one. Second, the goal is always the same. You're just trying to predict the most likely outcome. And third, you assume that there's a simple linear connection between those dials you're tuning and the data you're looking at. And that's it. Those three choices define the recipe. And this table just brings it all home beautifully. Just look at our two models side by side. Inside this GLN recipe, the only thing that really separates them is that first ingredient, the probability assumption. For linear regression, we pick the bell curve assumption because we're predicting a continuous number. For logistic regression, we pick the coin flip assumption because we're predicting a category. Just by changing that one single ingredient, the whole recipe automatically spits out the perfect model for the job, a straight line in one case and that S-curve in the other. It's incredible. So it turns out that underneath all the seemingly complex math of machine learning, there's this really elegant and simple structure hiding in plain sight. If all these powerful algorithms are just different dishes made from one core recipe, it really makes you think, now that you know the basic ingredients, what's the next problem you'd want to teach a machine to solve?